Good morning. For the past 2 weeks, we've been looking at equilibrium, examining what equilibrium is and how the concept of equilibrium connect to chemistry concepts. Zooming out here, what we have is our original slide deck and some of the things we've talked about. So we talked about equilibrium being a dynamic process. We've talked about how the reactants could be favored in a reaction, although it's proceeding in both directions at the same time. How there's this competing force. One's for the forward reaction, one's for the reverse reaction. The specific example there was acetic acid, where it ionizes in one direction, then it forms the acetic acid covalent molecule in the other direction. This ratio of products and reactants gives us a KEQ value. We can use the KEQ value to come up with some specific values for concentration, or vice versa. That was our first KEQ example over here. We're going to get to that a little bit more today. We talked about graphing and how that works with reactants decreasing over time, products increasing, and how the rate is going to level off in equilibrium, but the concentrations may or may not. We looked at Le Chatelier's principle, what we know about how concentration changes with time, and then the role of temperature, Le Chatelier and concentration again, the role of pressure, how the system will shift to the side with fewer moles if the pressure is increased, and vice versa if the pressure is decreased, and also the role of a catalyst. What we're looking at today now is branching off to analyzing a system is what happens when a system contains both reactants and products. Well, when a system contains both reactants and products, we don't know if it's necessarily at equilibrium. We can't assume that. We do know that KQ is still a ratio of products to reactants, but we don't know if these products and these reactants will give us that KQ value. The product and reactant ratio will only give us KQ if the system's at equilibrium. However, we might have caught the system as it's going towards equilibrium, or as it's just had new reactant or product removed, or some other type of scenario in industry. So if a system's state is unknown, whether or not it's at equilibrium, but we're given concentration values, we can look at the profit to reactant ratio and compare it to KQ. What we do is we call this Q. Write an equation for this. And that equation would be a Q, products over reactants. And I believe I might have said profit a minute ago. Perhaps Freud has something to do with that, who knows. Either way, we have Q, products over reactants. Now, products are going to be C to the C, D to the D over reactants, A to the A, B to the B, as we've seen previously. This value Q is going to compare our current conditions with our known equilibrium conditions. We have three possibilities here. In the case of Q, we have a value greater than KEQ. When we're trying to figure out what's happening, our easiest example to compare to is a situation where KQ equals 1. And I'm going to write that as being 1 over 1, because KQ being 1 over 1 tells us we have an equal amount of products and reactants. Easiest scenario to imagine. In the case here where Q is greater, a possibility would be 2 over 1 is greater than 1 over 1. Because the 2 over 1 represents products, what we see is that we have too many products, too few reactants. If we were to shuttle some of our products to become reactants, say this dropped down to 1.5 and that was 1.5, we'd end up with our KQ value of 1 over 1. This means we have too many products. In this case here, they're the same, so we're at equilibrium. In our third case here, unfortunately there's a little bit of a typo, so we'll correct that. If Q was less than KEQ, what must be happening?
Anyone?
Well, it looks like none of you are going to answer, so I'll just continue. If KEQ is greater than Q, we can set up a scenario that demonstrates that. So if KQ is 1 over 1, a number that's less than that would be 1 over 2. And just keeping things really simple, this means that we have too many reactants now, not enough products. So in this scenario, we would have too many reactants. Likewise, we're going to have an adjustment. That adjustment is going to be a shift from reactants to products. It's going to shift to the right. This one over here shifts to the left. So we'll say shift, right, shift, left. A couple years back, someone was answering this question like this on a quiz. They forgot the F in shift. Definitely remember the F in shift. Now we'll take a look at an example. Gaseous sulfur dioxide reacts with gaseous nitrogen dioxide to produce sulfur trioxide and nitrogen monoxide. At equilibrium, the respective concentrations are 4 molar, 0.5 molar, 3 molar, and 2 molar. Part A, determine the KEQ. KEQ is still products over reactants, but we're not quite sure of our products and reactants, so we're going to take a minute and we're going to write this out as a chemical equation. So, sulfur dioxide reacts with gaseous nitrogen dioxide to produce sulfur trioxide and nitrogen monoxide. Ensure you include the states. Everything here is gaseous. I'm not going to because my dexterity with this tablet pen is poor at best. So we're going to take this equation, look at it, confirm that it's balanced. 1 and 1, 4 and 4, 1 and 1, we're good. And then we can start working on KEQ. Now it says our respective concentrations are these values respective, which means that this is 4, that's 0.5, that's 3, and that's 2. So KEQ is still products over reactants. So we're going to deal with the concentration of sulfur trioxide up here, the concentration of nitrogen monoxide, and I do hope you're working through this at the same time I am. Sulfur dioxide and nitrogen dioxide. Those are the reactants. Putting in our values, we have 3 and 2 on the top, and we have 4 and 0.5, 0.5 on the bottom, giving us an overall value of 3.0. So KEQ is 3.0. So 3.0. Part B says to us, determine Q when 1.5 moles of nitrogen dioxide is added. Which way will the reaction proceed? So the reaction is going to proceed likely in the direction of the products because we're acting reactant. We can tell that before we do any calculations. If this is at equilibrium, which we know it is, and we add reactant, it's going to proceed to the right. It's going to shift to the product side. Our Q now we can calculate the same way we did before. Q is products over reactants. We still have the 3 moles per liter, the 2 moles per liter, divided by the 4 moles per liter, and our now 2 moles per liter on the bottom. So the question may come up here. We're given concentrations in the question, and then we're told that a certain number of moles is being added. These aren't interchangeable, and that's true. However, what the assumption we're forced to make is that we're dealing with a 1-liter system. And in organic chemistry and equilibrium, a lot of these systems we're dealing with are going to be 1 liter every single time. Now, adding or evaluating this, we end up with a Q value of 0.75, and we can see that our Q value here is less than KEQ. We have too many reactants, as we saw previously. It's going to shift to the right. So our suspicion was validated. Mathematically, we've proven that, and it's going to shift to the right. So you'd write that afterwards. Shift to the right. Oh, it looks like a person. There we go. All right. So it's going to shift to the right. C says, determine equilibrium concentrations for the scenario in part B. In order to determine equilibrium concentrations, we're going to use KEQ and an ice table. As a recap, an ice table has initial concentrations, the change in concentration, and then finishes with those equilibrium values. Our ice table is going to have the equation across the top. Sulfur dioxide reacts with nitrogen dioxide to produce, in equilibrium again, sulfur trioxide and nitrogen monoxide. Initially, we're told that we have 4.0 molar sulfur dioxide, 0.5 molar nitrogen dioxide, 3.0 molar sulfur trioxide, and 2.0 molar nitrogen monoxide. Our change is going to be a decrease of X, an increase of 1.5 that we added, which caused the decrease in X. And if this side is decreasing, the other side must have the opposite process. If this is decreasing, over here it must be increasing, minus plus X and plus X. Notice there are no coefficients in the front, so these X's do not have coefficients either. Finally, our equilibrium expression rose. Here we have 4 minus X 2 minus X, coming from the 0.5 and the 1.5 added together, 3 plus X, and 2 plus X. So take a minute and make sure those are your values in your table. If you haven't written it down so far, do it yourself and see where you are. In a minute now, we'll take a look at substituting this into KQ. So pause it and make sure you're up to speed. Now that we're comfortable with setting up our ice table, we're going to scroll down and continue solving for equilibrium concentrations. So our equilibrium concentrations, what do we know? Well, we know, as before, that KQ is the ratio of products to reactants. In our case here, our products are the sulfur trioxide, the nitrogen monoxide. So our KQ expression is going to be equal to 3 plus X multiplied by 2 plus X all over 4 minus X multiplied by 2 minus X. These are from these parts right here. So all that information is given in the ice table. We're putting it together. Mathematically, all of this is going to equal 3. And that came from the first part of the question, where we were given equilibrium conditions. So our new system, reactants and products, will balance out to meet equilibrium conditions. We now have to solve for X. So evaluating this expression, or starting to, 2x minus 2x squared minus 23x plus 18 equals 0. This is the point now where we need the quadratic. This is important because there are 2 ways we can address this. We can address this first by plugging in my computer that's dying. The first way we can address this is to use the quadratic formula as you would in math, and that will get you 1 mark, no problem. The second way to address this is to use a quadratic solver. So there's a function on your calculator that you can press where you can enter the a, b, and c values for this equation, and it will give you the 2 roots of this equation. You'll find out using a quadratic solver that's 10.7 or 0.85. Pause the video now, look up your calculator manual, and see if it's programmable and if it has this equation built into it. If it does, you're going to save yourself a ton of time, because you working through this with a quadratic formula for 15 or 20 lines and getting your x values is worth one single mark in grade 12 chemistry because you solve for x. Make sure your calculator can do it for you. Next thing, once we have these values, we have to figure out what to do with them. Well, we're going to take these values and finish off our problem by substituting these values in up here. Some of these values will make sense, some of them will not. For example, if you take 10.7 and you sub it in to this equation here, we end up with a negative 8 concentration. There's no way that can be right. That doesn't make any sense. Therefore, this is our root that mathematically works, but in reality doesn't. So this is going to be our correct answer here, and we'll substitute in the 0.85 for here. An answer less than 4 makes sense. Here, answer less than 2 makes sense. Here, an increase, and here, an increase, finally 2.85, are going to be the values that we need for equilibrium. So we can work our way through the rest of that, substitute for values, and then we find out our equilibrium concentrations. So yes, we do have to use the quadratic. The good news is it's just like math class. And as you would expect, though, it does get a little bit more complicated in the next example.
Simon's got a clue what's going on.